morning. Today we begin a new chapter, that is on precipitation from solid solution. Now, by controlling the precipitation process from solid solution, you can control the microstructure as well as properties of the material. And maybe I will go to this display here. Now, under this we will look at terminal solid solution, we will look at thermodynamics and kinetics of the process of precipitation, we will learn about spinodal decomposition, we will look at homogeneous and heterogeneous nucleation, we will also learn about the types of precipitate that we come across, and main purpose of all this is to get some additional strengthening in the material. So, we will look at precipitation strengthening, the mechanism of strengthening, and we will learn about few commercial alloys. Now, normally if you look at solid solution, the typical phase diagram looks like this. Here you have liquid phase, and in between this is the liquidus, this is the solidus, and here you have solid solution. There is no precipitation here, this is a pure isomorphous system, and if you look at the properties, you will find somewhere intermediate alloy we will have maximum strength. So, that means any alloy addition that you add element B to A, in that case strength of A increases. Similarly, if you add A to pure B, strength of B increases, and normally it is found that is some relationship between the strength of the material and its melting point. Higher the melting point, strength at room temperature is higher. So, that is why it is shown like this, and this is the optimum composition where you have the maximum strength. Now, what happens if you have a two phase structure? Now, within the terminal region of that solid solution here, both here and here, the strength will increase. So, this is the contribution of solid solution, and in between what you have mixture of two phases alpha and beta, and within this region the process of strengthening is one of, you can say something like a composite strengthening. So, its strength increases from here to here like this. So, if you have, that means strength increases, if beta is stronger, then with increasing volume fraction of beta, strength of the alloy increases. Now, we will see what happens if we are able to control the nature and distribution of precipitates in a terminal solid solution, where the solubility, in this particular case the phase diagram, it shows the solubility, this is the solvus line, here solubility is independent of temperature. Now, suppose this plot would have been like this, then how would we be able to control the structure, or how does the structure evolves in the terminal solid solution, and that is what we are going to look at in today and maybe another class. Now, let us look at a terminal solid solution. The diagram is shown over here, and in this case if you try and look at this diagram, here you have liquid, this is the two phase region alpha plus liquid. Now, you have an alloy, and if you are cooling it very slowly, what you have in between, you have pure single phase alpha. So, that means you only have the grain boundaries of alpha, you have this grain boundaries of alpha in the microstructure. Now, what happens when you temperature goes below this solubility limit? Now, here the stable structure is alpha plus beta. Now, beta will try to nucleate and we will see where will it nucleate. If it nucleates somewhere here, you will have a new surface being created and this surface will have an energy associated with it. This energy is this. Whereas, the extent of supercooling, when it comes over here, you can say this is the driving force. The supercooling is the driving force for the reaction and the total energy change at any particular temperature, what you can write an equation something like this, delta G. This will be the volume of the precipitate. If it is sphere, its volume is 4 pi by 3 r cube. There will be, this is the free energy of transformation per unit volume and this is usually negative because here thermodynamically this is more stable, whereas surface energy, this is the surface area gamma. So, usually what happens, this energy is positive. So, right over here you find that net free energy is positive is positive. It is because right over here at the solver's temperature, that means at solver's delta G V, this is equal to 0. So, therefore, total free energy change is positive. So, as you cool, here the transformation is not likely to take place. As the temperature goes down, there is a positive, there is a driving force, there is a negative free energy, and at certain temperature you will find this becomes 0. So, once this supercooling exceeds a particular critical value, then the process of precipitation will continue. Now, when we write this equation, we are making some assumption that here that whatever that precipitate that forms beta, the volume, there is no change in the density. So, density, that is rho of alpha is equal to rho of beta. So, in that case what will happen, there is no volume change, but usually this is rarely satisfied, there will be some volume change and there will be some strain energy, because outside also is a solid, this is a solid, this side is solid. It is, there is a slight difference between solidification and precipitation. Now, when we looked at solidification, there also we applied the same principle to explain why supercooling is necessary for solidification, but in this case there is a slight difference. When a precipitate forms, actually it will not be allowed, if it has a lower density, it will not be allowed to expand. So, how do we take this into account? That is the key to the process of strengthening that results from this precipitation. Now, if we look at the history, so there is a, if we look at the slide here on the computer, this is the historical perspective which is given. The interest in precipitation process is derived primarily from its effect on strengthening of alloys. And this was discovered, like most discoveries of alloys, it was discovered accidentally by Wilm while he was studying the solid solution strengthening of aluminum copper alloy by adding magnesium in 1906. In fact, that aluminum, the discovery, that is bulk, it was available in bulk towards the end of 18th century, and during that time you know that aviation also there was keen interest in developing aircraft, and aluminum happened to be a very light alloy, and it was thought that this can help promote or help in the design or newer generation of aircraft. So, there was a lot of interest in improving the strength of aluminum alloy, and the process of strengthening that was known then was a solid solution. And when he looked at some of these alloys, he found if you quench, the purpose of quenching was by quenching you can suppress precipitation, and then you can keep more amount of magnesium in the solid solution, and logic was if you keep more amount of alloy element in the solid solution, the strength should increase. But in his case he found that there was no increase in strength, but the quenched alloy it was left after quenching for few days, and then suddenly one day he tries to find out the hardness of that. He found the hardness increases and increases with the time of aging. This is how the commercial precipitation hardening alloy was discovered, and duralumin was the first commercial alloy which was produced in 1909. And this is the composition. It had the 3 to 4% or around 4% copper. It had say some amount of magnesium, little bit of manganese and some impurities, some amount of iron and silicon, and these are all in small amounts. And people wondered why does the strength increases. At that time, to look at the microstructure only optical microscope was available. Now, America was the first to suggest in 1920 that increase in strength is probably due to some submicroscopic precipitate which form below the solver's temperature. But this was proved, this was only a surmise. He just put this as a postulate, and this was conclusively proved only with the help of electron microscope when it was available, and the technique of sample preparation and examination of sample and transmission electron microscope was possible, and this happened in 1950s. And thereafter there has been considerable work in this area, and we will see how we can control the process of precipitation in these solid solution, this unstable solid solution, the unstable terminal solid solution, to get the maximum amount of strengthening. And we will see how that extent of strengthening will be controlled by controlling the phase transformation or precipitation process in this alloy. Now, let us look at the terminal solid solution here, and what happens if you take this and if you heat it, say suppose take this alloy and at room temperature, suppose this is its microstructure. You have this area is say if you take a supersaturated solid solution and look at this, this is the microstructure at room temperature. Here this is alpha and these are the precipitate beta. This is the equilibrium structure at this temperature. Now, suppose you heat it to this point. Now, what happens if you keep it for some time, the beta will dissolve, because the phase diagram it says that this is the region where same alloy should exist in a single phase form. And now, say suppose you cool it very fast. So, that means you have heated heat here, this is the solver's this temperature, and soak it for some amount of time and then quench in water or cool very rapidly like this. Then it is there is every likelihood that you will get a supersaturated solid solution. So, what does supersaturation means? It means by force you are keeping a large amount of solute in the structure. So, something like this. This is the excess amount, this is the equilibrium, so, this is the solubility limit at room temperature, let us say, and by force we are keeping this is the amount of solute. So, that means in terms of the excess solute present, we can say this is the excess solid, which is excess solute atom which is present in the solid solution. So, this is a measure of instability, you can say, and other way we can say we have a supercooled system and this is the temperature difference. So, this you can say is a measure of instability. Now, this process of taking forming a supersaturated solution, it is known as solutionizing heat treatment. So, here you soak it, you are giving solutionizing and then you are quenching, and by this process it is possible to get an unstable solid solution. And now, what happens? We will see how we can control the process of precipitation and supersaturated solid solution. Now, if you look at the free and recall the free energy composition diagram, somewhere here let us say when you have say at this particular temperature, so maybe it is easier to explain. This is the equilibrium structure and we have a supersaturated solid solution. Now, let us say the free energy composition diagram of that supersaturated solid solution is given by this curve. So, this is the free energy and this is composition, that is atom fraction B in this direction. Now, this is the solubility of B in alpha at room temperature. Now, here we have kept this much of excess. So, this is the amount of solute in alpha prime. We call the supersaturated solid solution as alpha prime. Now, for alpha prime its free energy is this. So, what you have, this is the free energy difference. So, its stable structure, it is made up of, this is the composition of atom fraction B in alpha, this is the atom fraction of B in beta. So, these two, this is the mixture of alpha and beta is the equilibrium structure at this particular temperature, and here by force we have kept this at room temperature. So, there is a measure of some amount of instability and this delta G, we call this as delta G V. This is the measure of instability and this is negative at room temperature. So, there is a driving force, but why it has, if there is a, and it is quite large, if this is the temperature difference from this to room temperature, if this is the temperature difference, it is quite large. Why does not the precipitation take place? And this is, to understand that, let us look at this diagram. Let us consider we define the driving force, that free energy change delta G V is the driving force for precipitation, and this can be measured either in terms of this extent of supercooling, that is the delta T. So, this is the temperature from which it has been quenched, and after quenching, let us say we have got the supersaturated solid solution and then we keep it at a particular temperature here and leave it at that temperature. What will happen to the microstructure of the alloy? And to understand that, say let us see, so this is at this temperature, this is the solubility. So, what we can say under this condition, you have either this you can say is the driving force or this is a measure of the driving force, and they can be converted to free energy, that is delta G V, and this is negative. But yet precipitation does not take place. It is something like this. This is the supersaturated solid solution and this is the equilibrium structure. There is, this is negative, this has a lower temperature, but always any phase transformation or from kinetics point of view, we know that unless it covers this energy hump. So, there is an activation hill, this must be overcome for the process to continue, precipitation process. We will see the origin of this activation hill, why do we have this activation hill. But it is very easy to follow that that microstructure, optical microstructure examination will not show any sign of precipitation, but you can follow the transformation by measuring hardness. This is the viscous hardness, and if you measure the viscous hardness at this particular temperature after aging at for different length of time at this temperature, then you quench it to room temperature and measure the hardness. You may find if this is the your as quenched hardness, and if you age you will find this hardness goes up, passes through a peak and then it comes down. Similarly, if you change the temperature of aging, you will find say if you age it at an even lower temperature, then you find you get even a higher increase in hardness. Now, we will try and see that means effect of increasing temperature is that hardness peak increases, peak hardness, say hardness, this is peak hardness, this increases as aging temperature decreases, and the time at which that peak hardness is reached, this is lower, higher the temperature. That means, the process of precipitation is faster at a higher temperature. So, therefore, the peak is attained faster, but so therefore, to get the full benefit you have to optimize, the aging time and temperature, so that you get an optimum strength which is usable, which has a proper application. Now, let us see the process of precipitation formation in a little more detail. Now, let us look at first homogeneous nucleation. So, assume a precipitate is forming, and which I just mentioned right in the beginning of the class. This is an alpha grain, and here you have a precipitate forming. So, process of formation of precipitate is creation of a new surface, and let us say alpha beta is the surface energy, per unit surface, and here we mention that the total free energy change will be sum of these two, and process will be spontaneous only if this free energy change is negative. Now, we mentioned that when you to get a proper expression for this, we must look at the contribution of strain energy, which is very important. The precipitate that forms may have a different density. So, there will be some amount of volume change, and this volume change results in additional stored energy, and this stored energy you can say this is a strain energy which is proportional to volume. So, therefore, the total free energy change apart from the volume free energy change, we must add the strain energy component, and for the precipitation process to take place, this total free energy, that is total free energy should be negative for the process to continue. Now, let us look at the classical nucleation theory. Now, there is a one point as we go through, we will find that when we look at the precipitate in an optical microscope, we see that after aging there is no precipitate. So, that means precipitates are extremely fine, and when it was possible to see them under electron microscope, they were of a much smaller dimension, something like maybe 50 angstrom on a nanometer dimension. So, therefore, people question that at that level will classical nucleation theory be applicable, because at smaller particle it is more likely that they will follow continuum mechanics. But yet many of these process of precipitation process, that phase transformation kinetics, whatever that experimental trend that we see can be very well explained in spite of this conceptual limitation that precipitate size is very small. Yet most of the features that we observe under experimental condition in a number of alloy systems, the classical nucleation theory can explain that very well. Now, a quick look at this, if we see that if r is the radius of the nucleus, this is the bulk free energy per unit volume, this is the gamma, and you can quickly write this. And I will leave it to you, because it is exactly the same procedure. If you look at, if you differentiate this total free energy at a particular temperature is a function of the size of the nucleus. And what will be a stable nucleus? How will you find the stable nucleus? So, what you do, you differentiate this, equate it to 0. If you do that, and with a little algebraic simplification, you can derive easily, and you can show that critical nucleus size is twice gamma, that is surface energy, gamma alpha beta, over the sum of the free energy, bulk free energy for transformation, plus the strain energy contribution. And similarly, this is the energy hum, this is the magnitude of that, this is the activation hill, you can say. And I will leave it to you, you will be able to, this is a very simple derivation, we have done it similar derivation during solidification. Now, if you look at this critically, what is important to recognize that this is negative and this is positive. So, what will happen? So, here r star, that critical nucleus size, what will happen if that strain energy increases? If strain energy increases, in that case this denominator, the magnitude of the denominator will become smaller magnitude, because this is negative, the magnitude will become smaller, the r star will be larger. So, what it means is that the critical nucleus size will increase. So, which is shown over here as the strain energy increases, this delta G star, that activation hill will increase, the critical nucleus size will increase. So, that means the process of, you can say, the precipitation will become more difficult if the strain energy, if there is a high energy of high amount of strain energy as a result of precipitation, if that strain barrier is to be overcome, you need to give more amount of thermal activation. So, that means in a way, and in another way, if you look at it, if we can play with this surface energy, if gamma decreases, then what happens? then critical nucleus size also decreases. So, that means you can by playing, but with alloy addition or alloy design you can play with it is possible to change both the surface energy as well as the strain energy, and by controlling that it is possible that we can promote homogeneous nucleation. Homogeneous nucleation will be promoted. When will it be promoted? If gamma is very small and the ES, the strain energy, is also very small, and we will see as you go proceed through the lecture when will it be possible to promote homogeneous nucleation. And why we will need homogeneous nucleation is, if we want that, we will see as we go through the mechanism of precipitation in any microstructure. These are the grains, you have this grain, and we know that strength of these grains can be improved if we can make the movement of dislocation which moves through the grain more difficult. So, if you have more amount of precipitate within the grain, so you need to have not only precipitate in the grain boundary, you will need to have lot of precipitate within the grain. And how can you get that? Means you have to suppress, because the grain boundary provides a favorable nucleation site. So, normally precipitate will like to form here, and primarily these grain corners and the grain faces. Now, to get a good precipitation strengthening, you have to have nice array of precipitates within the grain, and this can be promoted by promoting homogeneous nucleation. And now, let us look at a little detail the process of heterogeneous nucleation. Now, when this heterogeneous nucleation takes place, one of the preferred site is, this is the grain. So, this side is a grain alpha, this is grain, and here you have, this is the beta precipitate which has formed. Now, if we say that this is the angle here, it subtends the angle between these boundaries alpha and beta boundary here, and so these are surface tension, and at this point the force of they should be in equilibrium. So, that means this relation should be satisfied, that is gamma alpha alpha, that is force acting along this boundary, this should be equal to the force acting in this direction, and this is the component, the horizontal component of gamma beta cos theta twice. And when a new precipitate forms here, what happens? In a grain boundary, you have, this is alpha, this is alpha. Say if a precipitate beta forms here, what happens? So, this amount of alpha alpha boundary disappears. In its place, what we have? We have certain amount of A alpha beta created. So, this is one A alpha beta, this is the other A alpha beta, and assuming this shape to be a spherical cap, say this is a part of a sphere, and we call it, this is also a part of a sphere, and this is a double spherical cap, double spherical cap. So, assuming then this to have this type of shape, it is possible to calculate what is the increase in area or changes in area, and what is actually the change in the surface energy as a result of this type of a heterogeneous nucleation of precipitate, and you can show that under condition what will be the critical nucleus size, and if you go through the exactly the calculation procedure is exactly same. You have to consider this is the free energy, the driving force for the process of precipitation, this is the strain energy, this is the increase in surface area, that twice alpha A alpha beta. So, this is times gamma alpha beta is an increase in surface energy, and this is the surface which is lost. So, gamma A alpha alpha area is lost, and this is the energy which is lost. So, in this way you can write the full expression. Now, you can also find out easily the volume of the double spherical cap, which is given here, the area A alpha alpha, that means area of this circular shape, this circular area, this is A alpha alpha, which disappears as this, and new alpha beta area which is created, this is that. So, if you go through the steps and you can show that the heterogeneous nucleation, the dimension of their expression for heterogeneous and homogeneous nucleation will be exactly the same. So, whether it is heterogeneous or homogeneous nucleation, that dimension that is the radius of this critical nucleus is same, but that does not mean that volume of the critical. Key thing is the volume here is only of the nucleus is only this much, only this is the size of precipitate which needs to be created. So, compared to homogeneous nucleation, that volume of that precipitate that forms is much smaller here. So, that way, and the heterogeneous, this energy hump, you will find that this energy hump is a function of this shape factor. This function of theta is called a shape factor, and heterogeneous nucleation, that energy hump reduces. So, that means this is for homogeneous, this is for homogeneous, this is for heterogeneous. So, for heterogeneous process the energy hump is less. So, this is should be the normally the most preferred process of precipitation, and you can try and find out for different values, say put different value of theta in this shape factor, and see it is also possible to make it. Can you make this when is this 0? I leave it to you to do it. So, that means in such cases if this is equal to 0, in that case virtually there is no activation hill. And a quick look at the magnitude of this surface energy or nature of the surface energy, which is demonstrated here, which is shown in this slide here. If you plot, just make a plot of this gamma alpha beta against gamma alpha alpha. If you plot this, so when this is at theta, when theta is equal to 60 degree, cos theta is half. So, you will find that here this ratio is 1, whereas if the angle is less than 60 degree, this is less than 1. And also this magnitude will also depend on it depend primarily it depends on that shape factor. This will decide the theta, this magnitude of theta, or you can say since theta is related to the ratio of the surface energy, that will determine the shape function. And if you look at the heterogeneous, the volume of these two, you can easily show the volume of heterogeneous, that activation hill over homogeneous activation hill, this is exactly equal to the shape factor, and this is also equal to the ratio of the volume of the critical nucleus under heterogeneous condition and volume under homogeneous nucleation, these two. And if you plot these two ratio against a function of cos theta, then if the precipitation takes place in the bulk, then this will be the nature. If the precipitation takes place at the grain boundary or grain face, so that means here, in that case, that means edge of the boundary, then this will be the plot, and if it forms, can form on the grain edges, these 3 grains which are meeting. So, this is the nucleation, this is what we consider that this type of precipitate. So, I will call it, this is 1. So, this represents 1, this grain edge, this represents, this is the 2, and this is 3. So, this represents given by 3. So, that means the preferred site will be the grain corners, heterogeneous nucleation, and in that order, and in a 3 dimension you can see that at a particular point in a 3D, the 4 grains they can meet at a particular point, and which is tried to show in this 2D diagram. So, it is something like distorted, that is a tetrahedron. So, this is one boundary, this is another, this is other, this is the third, and this is one of the edges, grain edge. So, this will be the grain corner, that 4 grain corner in the 3D will be the most important site, or next is this grain edge, this will represent an edge, and this is represent a grain boundary or just a grain face. Now, let us look at the nature of the precipitate. When precipitate forms, say this is a matrix, when a precipitate forms, it is quite likely that precipitation, this coherent, they can form as a substrate. That means, the coherent matrix, that means the matrix may form as a substrate and the beta may nucleate on this substrate. In that case, there is every likelihood that this crystal structure will determine the nature of the precipitate, and in one extreme case which is shown over here, there is a perfect lattice matching. That means, the dimension of the lattice spacing of a particular direction here in alpha is equal to a lattice dimension along a particular direction in beta. And when this happens, there is very little strain energy associated. In this case, whenever you have this kind of a perfect matching, we call the precipitate to be coherent. So, this interface is a coherent interface, and this will have least energy, surface energy. Another case, if you can say that the lattice parameter of alpha and beta, they are slightly different from one another. So, it is likely, that means, at that interface we can visualize as if you have an edge dislocation, which is shown over here. This is alpha, this is beta, this dimension is a little less than this. So, therefore, you have, they are little distorted. This is the lattice, that line which is shown, the lattice strain, and here you can imagine there is an extra plane of atom. So, which represents a dislocation. That means, the interface between these two precipitate is made up of a number of edge dislocations. So, this type of precipitate we call it partially coherent precipitate, and you can easily calculate based on the difference in this lattice parameter what is the magnitude, or this is the difference in the lattice parameter delta. A alpha, A is the lattice parameter of alpha, A beta, is the lattice parameter of beta along that particular direction. So, this is you can say a measure of that lattice strain, and in this particular case A alpha, lattice parameter of alpha is greater than A beta, and it is possible to find out if this is the lattice mismatch. You will find out that this mismatch is equal to that lattice parameter when this distance is say after a certain amount of distance, say over this distance you can say here there is a perfect matching, here there is a perfect matching, but half of this you have maximum mismatch. So, you can say that over you can find out, that means what will be the distance between these type of dislocation, grain boundary dislocation in this kind of partially coherent matrix, and this distance is capital D. An incoherent matrix, there is no relationship between the orientation or between you can say the lattice plane here and lattice plane there. So, in that case which is represented like this. So, this is an incoherent matrix. So, energy wise this will have the minimum energy, this will have intermediate energy, this type of boundary will have maximum energy. So, therefore, if we look back upon that strain energy, so this or that gamma, that concept, you can say the gamma which prevents. So, here you can say that since gamma is less, there is no surface energy barrier for precipitate to form, whereas in this case you have maximum amount of the surface energy barrier which must be overcome for precipitation to take place. So, this type of incoherent precipitate definitely it will take place on grain boundary, grain corner or grain edges, and this will have intermediate characteristic. Now, what type of precipitate it will be interesting to look at will be ideal for precipitation hardening. Now, we have just seen to get a good precipitation hardening, you must have uniform precipitate throughout the matrix, and low gamma, low precipitate that boundary energy and low strain energy will promote homogeneous precipitation. So, therefore, if you can promote this, in that case you are likely to get more uniform distribution of precipitate, and which can give you better precipitation hardening. Now, therefore, the condition for precipitation hardening is the most solid solution, terminal solid solution, where coherent precipitate can form, or there is some amount of strain energy also. In that case they will exhibit precipitation hardening. That means, by controlling a alloy system which has some metastable precipitate, some coherent precipitate forming with a low surface energy and some amount of lattice strain. In that case, these are the alloy which will exhibit precipitation hardening. So, today if we look at what we have considered is we looked at stability of supersaturated solid solution, we looked at stability of supersaturated solid solution, we also looked at homogeneous and heterogeneous precipitation process, and we have seen that if we can promote homogeneous precipitation, then the process precipitation distribution is more uniform and they are likely to give a better precipitation hardening. We looked at heterogeneous precipitation, we looked at the what are the potential sites of heterogeneous precipitation. Then we have seen there are gradations. The grain corner are the most, where 4 grains, that means in a 3D network, where that these are grain corners are the point where 4 grains they meet in space, in 3 dimensional space. So, these are the places where if a precipitate forms, there will be minimum disturbance in that or lowest that surface free energy change. So, they will be the most favored site. Next will be the grain edge and then the grain face. And we also looked at the type of precipitate and origin of what type of precipitate, what is coherent precipitate, what is semi coherent precipitate, what is incoherent precipitate. If any alloy system you have incoherent precipitate, you cannot get precipitation hardening. But if there is a chance of forming that precipitate, that coherent precipitate, in that case you get a precipitation hardening. In fact, these coherent precipitate which were first observed in aluminum copper alloy, they were first shown through X-ray diffraction technique, that there are precipitates, there are strain fields associated with the precipitates, and this was done by Gwynner-Preston, and therefore, Gwynner-Preston, it is known as G. P. Jones. So, these are metastable precipitate which initially form during aging. They are known as G. P. Jones, and these are metastable precipitate, and their free energy is higher, but because of kinetic consideration, because of that surface free energy consideration, they appear before the stable precipitates appear in the matrix. We also looked at effect of aging on hardness and strength. We also looked at if you overage, again the hardness decreases. So, this is where the precipitate becomes so coarse they can be seen under optical microscope. When you can see precipitate under optical microscope, you can say that it is an overage structure, it has lost its precipitation strengthening. And we also looked at the necessary condition for precipitation hardening. And in the next class, I think we will look at not only another mechanism for homogeneous nucleation, and also we will look at the mechanism of precipitation hardening and how the precipitate distribution, size and volume fraction of precipitate determines that extent of precipitation hardening. And we will also look at little more critically on the nature of hardness versus time plot during aging. So, in the next class we will take up this, and thank you very much.